So we understood about deep learning, neural networks. We talked about activation functions during our or in our last videos, and I hope those concepts are really clear to you. We are going to talk about gradient descent and all its concepts in today's video. And hello everybody, welcome back to my channel. And let's talk about gradient descent, types of gradient descents we have, why gradient descent is really taking a big role in case of your this whole deep learning journey. What is the role here? All we know that during our regression that gradient descent is a concept. Okay, there we have this global minima, local minima, all those points we talked about it. But it will make real sense right now when we'll understand right now. I mean, how it works exactly with the deep learning analogy. So let's talk about it. So gradient descent is an optimization algorithm. Optimization algorithm used to minimize loss or cost of a model. So what is the role or use of a gradient? We have algorithm used to minimize cost, right? That is what we know till now, correct? Of a model. It iteratively adjusts. What exactly is happening? It's not like in one shot it will reach to the convergence, right? It iterates its reading multiple times so that it can adjust weights and bias. All we know, right? In our forward propagation, we have weights and bias and activation function, which takes care and which acts as a unit, and we are reaching towards output. And my back propagation happens from output layer towards your input layer. So during that, we all know that weight updation is happening, correct? So that weight updation is happening based on the gradients. That is what we are understanding right now. So here, what I'm trying to say that during that phase, like from output to input, what it does, it iteratively adjusts weights and bias during that time. All we know that we have only two components, weights and bias, so it does that. And just imagine that there's a blind person. Like if I'll explain in real, in simple terms, just imagine that one blind person like was stuck in a hill area or in a mountain, and like not blind person, I can say blindfolded. Just imagine that you are blindfolded yourselves and you are stuck in a mountain. What it will happen that, and it's not like it's easy to come down, right? You need to take steps, each steps very carefully. You need to check the slope while coming down, correct? And you will reach like when you'll feel the ground underneath your feet, you will feel, okay, I am reaching to the ground level, and there it ends, right? And that step is happening iteratively, right? Like you are thinking, okay, I have to take another step, and I'm just feeling the slope, I am going down. So that is the same concept here, which I am talking about the gradient descent. Now let me show you one image on how it comes up, or how it looks like in real scenario. Just imagine that, underneath your bed sheet, right? There are so many things, maybe one few balls, small ball, a large ball. Just imagine that you have a bed sheet, and underneath there are so many different shapes of things are there, and because of that the bed sheet takes different shapes, right? And that concept is same here when I'm applying. So here I am talking about the complete data set. Just imagine that how the data set or the data points are getting arranged in space. You need to imagine that. And when you are taking one particular point at a time, just the way I have shown here, that it starts like, it's not like always, the error is less. So at the very initial point of time, it will start with one point or one slope. So when it is, happening like this, right, it's all happening based on the slope, right? So when it will start with one slope, then it will try to reduce its slope so that it can reach out to a minimum area or minimum surface point where it can stay there. So that is nothing but a gradient concept, and the same thing I have shown here. So if you see from this, it looks like this is your minimum point, right? So like it will try to drag itself and reach out to a minimum point, and that is nothing but a global minimum. And when it passes here like this, so these single points, right, each point till the point it reaches to the global minima, that is called a local minimum point, right? So we have two concepts. Global minima is a final point where I can say the dl by dw or the gradient is zero, like there is no slope, right? And that is nothing but the point where the weight you need to consider, and the error or the error is minimum or the error is very less, you can say, right? So that is the concept of a global minima. And one more point or one more word you might have heard most of the times, which is nothing but a convergence. What is convergence? Convergence, we have two terms, right? Converge and diverge. Converge is a point where things will accumulate, what I can say, it's a point where things are going to be reduced to a bare minimum point. But when you are talking about divergence, it diverges from the logic we are saying, right? So when we have two terms, one thing is gradient convergence and gradient divergence. So gradient convergence is the only goal we always used to look for, not gradient divergence. With gradient divergence, we will get exploding gradient problem, not the other one, like not no, it is not solving the gradient issue. It is increasing the problem with the divergence. So always we need to goal the gradient convergence. And let's understand the concepts of gradients right now. And to give you one short example, and like all we can say that analogy, right? I will give you one simple thing, that imagine, just the way I told it, imagine you are at top of a hill. I'm writing down that example so that it is going to, be there on your memory forever. Mountain. So when you are there in the top of the mountain, that means what it represents? It represents high model error. Just do not imagine in a short data points. Just imagine that you have lakhs and lakhs of data points, how they behaves, and the model is giving the errors for all those data points. So you are at top, or that's the initial point. Then you want to reach the lowest value, right? Because you need to go to your destination. So for that, you need to reach out to the lowest value. What is the analogy here? That means I want low error zone, right? But my fog prevents me to come down. So what it will do? You feel the slope of the ground, right? under your feet. Which is nothing but the gradient. That is nothing but a gradient. And you need to take a step on that direction. Right? And you are not doing it in a single go, so iteration is happening. That means you need to reach to the minimum point. Simple analogy, right? So you can keep this in your mind. Okay, this concept, like in interview they'll ask you, you can give this analogy of gradient. It is going to be very easy. Now we will understand the mathematical derivation of it. So what is the goal of my gradient, guys? To minimize loss, right? To minimize loss or error. So what we are doing? For a particular given weight, I need to minimize my loss or error function. So when I'm talking about loss and error, that's nothing but a loss function, right? So this is my loss function I got. Then what is the next step? We need to find the best weight, right, W, such that the loss is minimum. And what we know why weight thing is coming into picture here, guys, because the whole deep learning, right, the moment the input layer starts processing and the architecture is designed in such a way that the weight initialization, the weight management throughout deep learning, the weight thing is there. Every time the weight is getting increased, the weight is getting updated, the weight is getting added to the bias. So weight is also always there. And when the back propagation happens during that time, the weight should be best updated so that the loss will be minimum. That's why your weight updation is happening in back propagation, because it is updating weights based on the gradient. On all we know that what is the gradient? Gradient is slope of loss function, isn't it? And when I'm talking about slope of loss function, that means d of LW divided by dW, because I have my loss function and I am going ahead by getting the derivation for it. Now we will move ahead. And once that is done, we have update method, right? So once that gradient is calculated, we need to update the weight, and that is the main goal. And all we know that we have learning rate. So here what is the symbols for this? We have weight means the current weight, right? Then this is nothing but my learning rate, and dl divided by dw is nothing but your gradient. So now that thing must be clear to you, why gradient descent. So two words are there, one is a gradient, one is descent. We need to descent the gradient every time. That's why gradient descent. We do not have to increase it, we need to decrease the gradient. So it's a gradient descent. And from this, whatever we are calculating, or whatever the output we are going to get, suppose my gradient is positive. Suppose my gradient is positive, like after the derivation, right? This part, after this part of derivation of this part, if I'm getting the gradient as positive, that means my dl by dw is greater than 0. That means my loss increases. So we need to move left to decrease weight. Decrease weight. Very important point. Like, what will happen? Somebody will ask, what will happen when your gradient increases? Imagine that you're just imagine that by changing these. I will show you one example. It will be very clear to you. By changing these values, just imagine that your gradient is positive, right? That means if this is greater than 0, right, what will happen? My loss is increasing, and when my loss is increasing, let me draw it. It will make sense. This is your, so whatever we have seen in 3D, right? We have seen this in 3D, correct? This curve and all. I am drawing that same thing in 2D plane. So just think in that way. And what I have drawn, that one point starts here, then one point starts here, like that, right? So the same thing I'm drawing here. Okay, just bear with me. So what will happen? It covers these points, correct? So when the point moves, this is my left, right? This is my right. So when my loss increases, we need to move left. We need to move left. That means we need to move from the left side, not from the right side. We need to decrease the loss. We need to decrease the loss, not to increase the loss, right? Next, if my gradient is negative, what will happen? It's opposite. Loss decreases. Move right. Increase weight. So this is the relationship between weight and loss. So if my loss is decreasing, increase the weight, because the proportion and the balance needs to be there. It should be maintained, right? So that's what. And now if I'll give you one example, it is going to be very clear to you. What we know, guys, we have my loss function. So suppose your loss function looks something like this. Then what is the first point? We need to compute gradient. So when I'm computing my gradient, what I am going ahead? I am doing d del by dw, which is nothing but, we know the differentiation, right? It will be 2 into w minus 3. Then I need to update my weights, right? That is the next step. And this step will happen iteratively, right? So w equal to w minus, so let me just take it. So all I have is w equal to w minus eta of 2 into w minus 3, right? This is the formula. Now all we have is this formula. Now let us imagine initial weight is 0. Initial weight is 0 and my learning rate is 0.1. Let's start with a smaller learning rate, and I'll tell you if smaller learning rate and large learning rate, what is the difference? I'll tell you that. So iteration will happen, right? Iteration 1. So before iteration, you have to know one more thing here, that what is the final weight and till what weight it is going to convert. So what is the goal, guys, here? In my loss, in my gradient descent, what is the final thing? That my slope or my gradient should be 0 to converge, right? So for that, I cannot set to 0, but it should be nearly 0. So for that, I'm just writing like this. So when I'm writing like this, what I have, 2 minus w into 3 equal to 0. That means w minus 3 equal to 0. W equal to 3. So I have got my weight. That means what we understood, at w equal to 3, my convergence is happening. So now we are doing the reverse thing. So I am seeing okay, to reach my weight equal to 3, how many iterations it is going to take. So that's what I'm checking right now. So my first iteration, suppose weight equal to 0, first iteration. So 2 into 0 minus 3, I am getting minus 6, right? Then I'll update my weight 0 minus 0.1 into minus 6, and I am getting 0.6 here. So first iteration over. Then the second iteration, it will take this weight and it will, calculate right now. So it's minus 4.8. Then I'm going to calculate W here. So 0.6 minus 0.1 into minus 4.8, which is coming 1.08. Then 2 into 1.08 minus 3 minus 3.84. W I am getting 1.08 minus 0.1 into minus 3.84, and I am getting 1.464. So just imagine that it will, it will increase and it will be ending up at nearly 3. So that means that point starts from 0, right? Then it went till 0.6, suppose. Imagine that. Then it went to 1.08, then 1.46, 1.08, then 1.46. Then imagine that it will reach to 2.1, then 2.7, then 3. So to reach 3, it took how many iterations? 1, 2, 3, 4, 5, 6. 6 iterations it took. And that is how my gradient descent forms. And here my learning rate is 0.1. So if my learning rate is 0.1, that means it is a slow learning, right? And if learning rate, if you take just 0.5 or something, then divergence will happen. And preferably this is not good, this is good, because you want your model to learn slowly so that it will always generalize the output. It will never give the biased output, right? So this is the whole concept of a gradient descent. Now we will understand what are the different types of gradient descent. So we have the first one. So when I'm talking about gradient descent, we have the first one, which is the one is batch gradient descent. So again, these all things are optimization algorithms, right? Optimization algorithm. And it calculates gradient of cost function using the entire data set. So it calculates the gradients of cost function, because we know loss function or cost function, that's what we have seen the calculation. And here the entire data set is being used. And if I'll draw the same thing, it's the same thing, guys. I mean, there is no difference. If this is your so it should touch actually once, like this. Then if this is a point, this is a point, this is a point, right? Then this is how the gradient forms. And just imagine that this is a point. So the slope, how the slope is being understand. So this is one point, right? This is another point. This is another point. This is another point. This is another point. And here the slope is 0 because there is no angle, right? Then again the angle increases, angle increases, angle increases, angle increases, angle increases. So you can see, I mean, how the slope, the tangents it is forming and the slope it is changing, right? That is your gradient descent. And you can say this is just, the understanding of gradient descent. Rather, like, there is no specific understanding of like how batch gradient descent. Until unless will not do any programmatic thing, you cannot see that difference as much, because this whole thing is same. And it is good. It is computationally expensive, though it is computationally expensive and slow, but it is being used in many cases. When you are considering small data sets, that case it is fine, but for larger data sets it is not. Next we will understand a very important concept, which is stochastic gradient descent. So if somebody will ask what is the difference between stochastic gradient descent and gradient descent, when I'm talking about gradient descent, like basically we are talking about batch gradient descent, but stochastic gradient descent is what? Again, it is a iterative optimization algorithm. Everything is iterative, right? Iterative optimization algorithm used to minimize loss function by updating weights. We know that. And what it is doing, it is using one or a few training samples. This is the major difference. So it is not using the entire data sets. And what it is doing, at a time it is doing that. And not taking the entire data set. Right? So this is your stochastic gradient descent. And as it is taking random samples, or taking at least one data point every time, the approach is faster, right? It's more efficient because of that, because you can just imagine that when you're using the complete data set, how much memory it's going to consume, but as compared to your very minimum, or at least one point, or some random samples at the same time. And as it is considering some random data, it helps escape the local minimum. And it is very ideal for large scale data and neural networks. So all we will do from now on, like in our practical implementations, we will use stochastic gradient descent, and I will show you how the gradient descent and stochastic gradient descent works in general by using the code. And how it happens, it starts with random samples, right? That is the first thing. Computes gradient Second thing, updates parameters or weights. Here parameters means weights. Then stochasticity or noise is the one which takes a great role, because it, while updating the path, right, it fluctuates as compared to your batch gradient. So if you'll ask me that how my batch gradient and how my stochastic gradient looks like, so just imagine that here a point is present. So this is your batch. But in case of your stochastic, how it is going to be? So if one point is there, it will be like this, like, sorry, my bad. It is going to be like this, then like this, like this, like this. So this is your batch, this is your stochastic, right? Then we have one more type of concept, which is nothing but mini batch stochastic gradient descent. Mini batch stochastic gradient descent. So what is it? It falls between batch gradient descent or stochastic gradient. It comes in between. What does that mean? So all we know that in batch gradient descent, it takes the entire data set. In my stochastic gradient descent, it takes one or a very few samples. So mini batch, what could be the sample size here? Just imagine. The sample size could be between 32 to 512 samples it can consider at a time. So with this, we understood how my gradient descent works, what is batch gradient descent, what is the major difference between gradient descent, stochastic gradient descent, how my mini batch stochastic gradient descent works. So we understood everything now, and we will meet during our next video. Please subscribe, like, share your comment, share your valuable feedback, share this channel link to all your friends and near ones. And while subscribing, do not forget to hit the bell icon so that you'll not miss the latest updates, and stay healthy, stay safe. See you till the next video. Bye. Thank you.